Hi, my name is Radek. I'm a manager of software engineering in Netsuite CX organization.
And my name is Louis. I'm a senior member of technical staff at Oracle Lab doing research on recommender system.
Welcome to our joint talk about Netsuite Recommender and its future in cooperation with Oracle Labs. What we're going to talk about today. We will start with what is NetSuite Intelligent Recommendation feature, what does it look like, what's under the hood, what we're working on to make it even better, and also what we're working on to make development of further machine learning features in NetSuite better in general. Last part, I will give it to Louis to talk about the exciting new recommender models that we are trying to get to production together. Let's talk about the NetSuite recommendation, intelligent recommendations. Before we start, however, let me quickly introduce NetSuite and Ecommerce. As you may know, NetSuite is the #1 cloud ERP system with over 30,000 customers. While ERP is arguably the most important part of it, NetSuite doesn't only do that, but rather it's a business suite that includes, among other things, CRM, HCM, and commerce. The flagship commerce offering is called Ecommerce, and it allows NetSuite customers to easily set up their commerce websites, and it's part of the suite, so there is no hard configuration needed. As I've mentioned, or should have mentioned, the official name of the recommender feature is Intelligent Recommendations, and it mainly lives in two parts of the system. First, it can be presented to our customer's customer on a Ecommerce website. This is your classic product area titled you may like or similar. We currently support 4 recommendation use cases for the website recommender, like checkout recommendations, session-based recommendations, transaction history, and we bought also bought recommendations. The second place where we provide recommendations is CRM. This is for sales representatives who can get recommendations for their customers when building a quote or sales order. The plan is that recommendations will live in many other parts of the system going forward. Let's briefly talk about 2 more customer-facing elements of the feature. First one is called recommendation scenario. It allows our customers to set basic business rules like item blocking, tweak some characteristic of the list of recommendations like diversity, novelty, and freshness, and see results in real time with a live preview functionality. Behind the scenes, all our recommendations are powered by these scenarios, but there are default ones that come out of the box, so our customers don't have to set it up manually. The last customer-facing part of the recommender I would like to talk about is analytics. These let our customers know how well the recommender widgets are doing in their customer sites in terms of number of impressions, click-through rate, and conversions. That was the customer-facing part of the recommender, and now let's peek under the hood and talk about what it takes to get something like recommender into production. When we first started developing intelligent recommendations, we needed a model. We pretty much ended up following this quote. This is not how we feel about recommendations today necessarily, but at the beginning of that project and at the beginning of any machine learning project, I believe we will go back to that. It proves pretty useful. Following that logic, took us to something called matrix factorization for implicit feedback. Matrix factorization is a group of recommender algorithms belonging to the collaborative filtering family, meaning that it uses interactions between shoppers and items to generate recommendations. The algorithm takes a matrix of interactions as an input and factorizes these into 2 smaller ones, one consisting of shopper factors, also known as features, and the other one of item factors. These 2 matrices are the model. In general, the 2 model matrices are much smaller in data size than the original data source, And therefore, we can say that shoppers and items are represented in reduced dimensions, and therefore their tastes are somewhat generalized, meaning the shopper taste. Getting recommendations for shopper means computing a dot product between a shopper vector and an item matrix, and ordering the result in ascending order. The item matrix is interesting by itself because it can provide item-to-item recommendations using a similarity metric like cosine similarity, or also dot product, Euclidean distance, and similar. The matrix factorization model is based on a paper from 2008, and it cannot really be considered cutting edge today. This is why we have been working on improving and ultimately replacing it. But more about that will be discussed later. Let's talk about challenges in developing scalable machine learning features like Recommender for a big system like NetSuite. As I mentioned a few moments ago, NetSuite has over 30,000 customers. So it's pretty clear we cannot set individual models and their configuration for thousands of customers by hand, because we would need an army of data scientists. All of these customers have in general very different data sets, meaning the customer accounts. They differ in number of shoppers, items, number of transactions, but also in data sparsity. We had to develop a way to automatically find the best model configuration. And we also had to introduce something we call model eligibility. I will go into details on that later on. Additionally, whatever the data set looks like today doesn't mean it's going to look similar in a year. In NetSuite, we hope our customers will grow, and we hope in a year there's going to be twice as many transactions in that account at least. Let's talk about how we represent a recommender model in our system in order to solve those challenges I've just mentioned. This is a simplified pseudocode of a model interface. It shows the properties that we need to know about every model and that every model needs to implement. Since recommender models are retrained pretty often, we actually prefer to use terms like model algorithm in favor of just model. And then what we call model is the product of the training algorithm or model algorithm. Every recommender algorithm has its name, and the resulting model has a set of supported use cases. A model algorithm has to have a way of determining whether a customer dataset fits the minimal model criteria. This is what we call eligibility. And finally, a model algorithm has to have a way to auto-adapt to changing dataset or find local optimum when first deployed. That means the model needs to be able to optimize its hyperparameters continuously. So next I'm gonna do a little walkthrough of how we enroll new customers. In NetSuite, everything starts at a enable feature page that is basically a form full of checkboxes where NetSuite administrators can enable features for their accounts. Currently, we only let customers enable the feature if at least one of our machine learning models is eligible. Once the feature is enabled, all those customer-facing parts from the first section of the presentation become available, but also a lot of things start happening behind the scenes. Models are set up with default settings, and a training task is triggered and scheduled for daily, or rather nightly training. An auto-tuning task is also scheduled. That's something we also do at night. Auto-tuning starts running regularly, trying to move the model hyperparameters closer to the optimum with every run. It never really stops running because datasets can drift, and we need to stay in the optimum for the current dataset. After the first training completes, the recommender model can be used. Before that, only fallback models are available, like popular items. After the first training, our customers can fully take advantage of the feature. Our current solution is embedded in Netsuite's Java application stack, and there's quite a few reasons to move it to a special infrastructure. This is what my last section is going to be about. Although building machine learning models is the most exciting and the glamorous part of machine learning feature development, it's by far not the only part. In order to deliver an end-to-end machine learning feature, there's a lot of other software to be developed. That actually represents the majority of the code, time, and effort that needs to be invested. If these parts are well designed, however, some of them can be reused in other machine learning features. And a lot of the infrastructure can be reused between machine learning products. And this is why we're pretty excited to move our machine learning to OCI Data Science. OCI Data Science is a cloud service that allows us to perform all needed AI experiments, as well as train, auto-tune, and deploy our models. And there's much more. This is exactly the shared combination of infrastructure and AI software that we need to develop the recommender and our future machine learning features more efficiently. Finally, here's how Netsuite works with OCI Data Science. So in Netsuite, we have built an ETL service that stands for Extract, Transform, and Load to feed the data to OCI Data Science. With data in OCI, we can perform AI experiments in Jupyter environment, or we can tweak our models on a big repository of datasets, develop new model training and model tuning pipelines. Those can be then deployed into production. OCI Data Science, it also makes it much easier to cooperate with other teams. For example, Oracle Labs. And with that said, let me hand it over to Louis from Oracle Labs.
Thank you very much, Radek, for the first half of this presentation. So now I will talk about the work we do at Oracle Labs. And if you have not yet heard about Labs, you can think of this as an entity within Oracle that takes over part of the research and development work and try to help all of Oracle products and customer have access to next-gen solutions, state-of-the-art solutions. So first, I'll talk about, so during this whole presentation, I'll talk about a library that we are building. It's an internal library, so it's not customer-facing. It's called a SANE recommender, where SANE stands for Smart Analytics Engine. And the mission for this library is to help all of Oracle's products, including Netsuite, to be able to have access to state-of-the-art recommendation engines and provide high quality recommendations to our customer. So we think of our work focusing on 4 pillars. The first pillar would be use cases, that we try to find as many use cases and fulfill as many use cases as possible by communicating with the product teams, with the customers to know what's needed. The second pillar is research, that we perform research, we learn from the public research, we listen and learn about the cutting edge to be able to create new state-of-the-art recommender system. Our third pillar is development practices. We want to have high quality development environments to provide code that is, first of all, extremely reliable, that will never fail, but also is able to scale at the size that we provide within Oracle. And our fourth pillar is for evaluation, that when we have developed a model and we have collaborated with internal teams to put this model into production, the work doesn't stop here. We continuously evaluate the model, and we build a mechanism to receive feedback from production environments, either, as Radek was saying, to automatically tune the models or to let us know what work is needed to improve our systems. So to fulfill the use cases of an enterprise recommender system, we designed this recommendation pipeline, which you could find similar thing in many usage for recommender. So in 4 steps, the first step is that our library provides tools to manage data specialized to the use cases for recommendations. So the type of management that's needed is, for example, managing data about items, data about users, but for recommendations, the most important are interactions between user and items. And we also add some other sources of data, such that contextual data, in what context a recommendation happens, which should inform what items should be recommended. The second part, and we could say the core of our library, is a set of retrieval models. So Radek already talked about matrix factorization previously, which is one of the models included in our library, but we also have other models from simple to more complex, and I will talk about these models in the rest of the talk. The third step is filtering, because there are things that are not necessarily done by models, such as blocking items that are not currently available for sales, or having other block lists for removing from recommendations problematic items, or even some filtering specific to the user. An example of this could be that we don't want an e-commerce recommender system to recommend alcohol for underage users. And after this raw filtering has happened, we have other models that score items to re-rank them. And we try to re-rank, of course, based on the preferences of the user with some scores specific to the users. But we also try to optimize metrics such as diversity or novelty, so that we are sure that users are not faced with a singular type of items and have the opportunity to find new things and interests provided by the recommender system. So now I'll talk about our models and why do we need in one library multiple models for recommendation instead of a single one. So one of the most common trade-off between models is the balancing between time it takes to train a model and the accuracy of the recommendation. So I'm talking about training because all these models are machine learning models that learn from data, learn from large quantity of data with some amount of computing time required. On the top right of this graph, you see the self-attentive sequential deep learning models that we have in our library. They are the most complex models that are able to model the most complex behavior from the users. So they achieve higher, most of the time, higher recommendation accuracy, but they also require a larger training time. And we keep in our library multiple models from most complex one to simplest one to be able to serve multiple use cases where sometimes we need a short training time and very fast recommendations, but sometimes we have the time to optimize for accuracy. And to talk about deep learning more specifically, it's really useful to us to have deep learning models in our library because recommendations is a task which requires to solve multiple use cases. Sometimes we provide recommendation with access to features about the users, sometimes with access to attributes of the items that we recommend, sometimes with different contextual information. And most simple models, they can ingest one or two of these sources of data. But the deep learning models can be adapted, and we have done that work to adapt deep learning models to be able to ingest all of these different sources of data. Additionally, the deep learning models, they can be more dynamic, and they can be fine-tuned to optimize different metrics such as diversity and novelty, as I was talking before. And they still provide, after being trained, a very fast inference time and high scalability. So now we'll deep dive into the details about some of our models. So here is one model that we find performs very well. It uses data about users, about items, and about interactions between user and items. It's composed of four different compartments. One of the compartments is a session-based user preference. This one is specialized to just ingest the most recent items from the interactions. So the most recent items a user has interacted with in order to be able to know what is the user interested in right now. The second compartment is the long-term user preferences, which ingest very long sequences of interactions of the user. And based on this, is able to understand the deep preference of this user, preferences that continue coming over time. And the third compartment is item style model, where it's simply a model that learns specificities of the items. So from this, we learn embeddings for user and for items, and then we use them in a similar way as what Radek was presenting with the matrix factorization. This user embedding and user item are aggregated into recommendations. A second model that is in our library of sequential deep learning models is using the concept of self-attention. So one of the strengths of this is that this model learns from user sequences of interactions with items, and the attention blocks are specialized to be able to guess which of these items in the sequences of purchases of one user are most meaningful to predict the following purchases of that user and to make next best item recommendations. Another use cases for this model is that it's very dynamic. So as soon as a user has interacted with one or two more items, this model can immediately be updated to recompute the state of the user and once again provide dynamically the next best item recommendations. So as I've been talking about multiple models and machine learning models that take time to be trained, other challenges that we are facing are around selection of models and tuning of model and evaluation of the models. So for this, we provide advice for model selections, not only based on the difference between recommendation accuracy and training time, but also on aspects such as the size of the data set, or in the case of recommender system, the sparsity of the data set is also very relevant. The second step after model selection is something that Radek already started mentioning, the model tuning. So of course, our models can be trained. This is the first step, but models also have what's called hyperparameters. So small parameters that change how the model behaves, and we need to tune these hyperparameters. So the solution we have implemented in our library is Bayesian hyperparameter optimization, which basically tries training and evaluating offline the model on some set of hyperparameter and then intelligently guesses which hyperparameter may perform better than the one currently being evaluated. And over time, this Bayesian optimization of the hyperparameters finds optimal hyperparameter for the model. We also included a large array of offline evaluation metrics to be able to measure anything that we want to measure to be able to evaluate our recommender systems. And the third step, if offline evaluation is useful for recommender system, but ask anyone using recommender system, they will tell you that online evaluation is what truly matters when measuring the quality of a recommender system. So we are also building tools that allow for constantly monitoring the quality of recommendations, but also to get feedback from production environments about the quality of our recommendations and to perform some automated A/B testing using techniques called multi-arm bandits in order to even better select hyperparameters of the models and select models themselves. So to conclude these talks, I want to remind a few of the achievements we have had. So first of all, we strive and we have been quite successful at adapting our library to fulfill all the needs of recommendations in enterprises. And other things I'm quite proud of is that we have built a library that scales to millions of user items and interactions to very large data set very quickly, and that we are able to provide high quality recommendations within 10 milliseconds of inference time. Thank you very much.